Good morning, physics. How are you guys? We're going to keep moving on, and today we're going to talk about moment of inertia. And the moment of inertia is an object's resistance to rotation. So torque we usually use to get it rotating or to stop it. And the moment of inertia, you remember inertia is it doesn't want to move or it doesn't want to stop. That was Newton's law. An object in motion stays in motion, and an object at rest tends to stay at rest. Well, this is the moment of inertia. The moment that that object is resistant to change in rotation. Mathematically, we use this kind of slanted I, and that stands for moment of inertia. And the units are derived from the equation, which is mass times radius squared. So the units are like kilograms times meter squared. So that is just going to be your unit. And sorry, my brain is about shut down. The definition in your book says the moment of inertia of a point mass is equal to the mass times the square of the object's distance from the axis. Yeah, that makes perfect sense, doesn't it? First of all, you're probably thinking, what the heck is a point mass? And so you know what I did? What the heck is point mass? So I tried to answer this the best I can think of. And basically, a point mass, it's like this abstract idea of a point, and this is where we kind of pretend, for the sake of physics, that the entire mass of the object is concentrated. We basically take the whole object and treat the entire thing as a single point. Let's take my Sharpie, for example. If we are doing a calculation, instead of describing this entire, I guess it would be like a thin rod, instead of talking about the entire Sharpie, we talk about it as though there's one point somewhere on the Sharpie and the entire mass is at that point. That's about as good as I can get, honey. Oh my gosh, honey. You can tell I've been talking to my kids all day. Anyway, that's kind of what point mass is. It's kind of you're imagining that the mass is in one point. Now, if you take a look on page 214, you are going to see this table. And this table shows you all of the different moments of inertia for various objects. And so you'll see that we use different formulas for different objects. And so there's that I'll go over just the way I had done it. So the moment of inertia for a hoop. So like if I'm making you measure a hula hoop, its moment of inertia, you just use m equals r squared. Just the basic formula. But what if you have like a solid cylinder that looks like that? Well, a solid cylinder is 1/2 mr squared. Or a sphere, like a basketball, it's 2/5 mr squared. What about the moment of inertia of a long rod? Kind of like a baton without the ends on it. That would be 1/12 ml, where L is length, ml squared, but that's only if we're talking about the center, like the center of the baton. Like if the axis is right there at the center. Well, what about a long rod with the axis on the end? That would be more like this. Like if we have the end of a long rod, then we're talking 1/3 ml squared. And if we have a little thin rectangle, it's 1/12 mass times L squared plus W squared, which that's width, and all of that divided by 12, or 1/12 times that. Okay. Lots to remember. The good news is you never have to memorize these. I just wanted to go over the fact that depending on an object's shape, we use different equations. Now, I want to talk about something. The example problem on page 215. It goes through a whole long series of how to solve for a baton, which, as I said before, that's a long rod, and we can do it in the middle of the rod or at the end of the rod. And frankly, they're not using the formulas that are given to us. So I'm not going to show you this because as I started to do it the way you should do it, when you have the 1/12 if it's in the middle and the 1/3 if it's at the end. This sample problem, there is nothing about this that actually abides by the right physics formula. So I don't know if it's a typo or if they're doing it in such a way that I'm overlooking it, but we're going to skip this because I'm frankly kind of worried that it's going to mess you up. I don't like the way it's explained. In fact, I'd appreciate it if you guys skip this problem as well, because I just told you, and the book just explained that this would be, the formula we'd use for a long rod, and yet they are just using plain old mr squared. So we're going to skip that one. Let's look at number 21 instead, and let me walk you through this. So we have two children of equal mass, and they are sitting 0.3 meters from the center of a seesaw. Now, assuming their masses are much greater than that of the seesaw, how much is the moment of inertia increased when they sit 0.6 meters from the center? All right, so we're moving our radius from 0.3 to 0.6. So we're going to double that, okay? How much are we increasing their moment of inertia? Now, let's see what we know. All we know right now is that the children have masses that are equal, right? Right. Yes, Dr. McKean, thank you. Nod sleepily, guys. And we know that their initial radius, they're both sitting at 0.3 meters from the middle of the seesaw. Well, what if their distance, their r, doubled to 0.6? Because remember, that's what it asks us in the problem. They want to take us from this r to this. Well, the easiest way I can explain that is, first of all, we know that the radius is squared in the problem. So if we double the distance, our inertia is going to be 4 times larger. But if you need me to prove that mathematically, that's what I'm going to do. So let's pretend each child has a mass of 10 kilograms because I want to keep the math simple. So I'm just going to insert this. Remember, I, moment of inertia, equals mass times radius squared. Let's look at their initial radius. 10 times 0.3 squared is equal to 0.9 kilogram meter squared. So this is their initial moment of inertia. Now we're going to double the distance. We're going to, instead of sitting 0.3 meters from the middle, now the kids are going to back up and they're going to sit 0.6 meters from the middle. So I'm going to plug in their mass, one child at a time. So 10 kilograms times 0.6 squared is equal to 3.6 kilogram meter squared. Well, 0.36 is 4 times larger than 0.9. And remember, if all we had was this and we said we're going to go twice the distance, it's going to be 4 times greater. If we said we were going to go 3 times the distance, then it would be 9 times greater. We've gone through this before where you're squaring things. And what if I said we were going half the distance? What's 1/2 squared? Good, so that would be 1/4 the moment of inertia. Okay, so you get the idea. All right? How about we try the next problem together?